This video is about use of the covariance matrix. Here's an example to define a multivariate Gaussian distribution for the Kalman filter. The basic question that we want to answer is, why are we using the multivariate Gaussian distribution? We won't get into the mathematics of the Kalman filter in this video. And this covariance matrix fully describes a multi-valued version of a Gaussian curve. So in the last video we talked about the Kalman filter, and we talked about Gaussian distributions that define the behavior of the sensors. In this video, our example is again going to be a robot. This time we're looking down on the robot. It has two rangefinders. It has this one, which is measuring this distance, and this rangefinder, which is measuring this distance. We call this one x1 and this one x2. So let's say this is a laser beam and this is a laser beam, and these are being used to measure two distances. It's a distance 3 and a distance of 2. Ideally, the sensor will not always give you the exact answer that you want. Now let's say we've determined experimentally what the multivariate Gaussian distribution is. So here's a multivariate Gaussian distribution where the covariance is 0. And for example, here's a covariance matrix. You've got covariance is 0, you have variance of 25 and variance of 9. So you can see variance of 25 means that this is longer in the x1 direction than it is in the x2 direction. That's because this variance of 25 is greater than this variance of 9. And it means that this x1 sensor is less precise than this x2 sensor when it gives you a reading. Now, what if the sensors were somehow related? We're not going to say how that happens physically, but mathematically we know that it could happen. That suppose if one sensor happens to give a value that's higher than the ideal, the other sensor also happens to give a value higher than the ideal. Well, in that case, if we characterize our sensors, we would get something like this. It's a different multivariate Gaussian distribution, and you can see here that supposing that x1 happens to be higher than it should be, the x2 distribution, right, this is x1, so the x2 distribution that you get if you limit yourself to being on the x1 line here is shifted over, so x2 tends to be higher too. So when x1 tends to be higher, x2 also tends to be higher. And when x1 tends to be lower than it should be, x2 also tends to be lower than it should be. Now if we had negative covariance, you'd have this situation where if x1 is lower than it should be, then x2 tends to be higher, and if x1 is higher than x2 tends to be lower. Okay, so let's say we have this situation with a positive covariance. And let's say this is our actual covariance matrix. Now the question is, could you get away with just using the variance of this sensor and the variance of this sensor to create this model? And it turns out that it's more useful if you have the covariance also, because these two pieces of information alone, these two just Gaussian distributions, don't give you as much information as that full multivariate Gaussian distributions, because they don't tell you anything about how the sensors might relate to each other. If you just have these two, this would only be fully descriptive if the two sensors have error that's independent. When we use a Kalman filter, we're going to need to know about the relationship between the error that the two sensors have, and that's why we need to know about the covariance matrix.